All right, so this question says find V1. So let's actually analyze the circuit first before trying to find V1. So it looks like we have a battery source here with 12 voltage, and we have the positive side of the battery, the negative side of battery, and we have the current over here, which is the electric charge, the flow of electric charge going this way, and then coming over here, going through resistor 1, and then going through resistor 2, before coming back around to the negative side, looping back around to the negative side of the battery. And we need to find the V1. We need to find V1 here. Now, V1 in this case is actually the voltage drop across resistor 1. What does that mean? Let's explain. Let's explore. So this right here is what's known as a series circuit. So a series circuit. Series circuit. The reason why is because we have two resistors here that are in series. What that means is that they're in one line. So you have series 1 here, and then directly after it, you have resistor 1 here, and then directly after it, you have resistor 2. And they are both in one line, so when the current goes through, it goes through R1 and then goes through R2 without there being any kind of break in between them. And that's how you know that it's a series circuit and the resistors are in series. Now, what's interesting about a series circuit and why we even care about that is because in a series circuit, the current remains unchanged as it goes through each resistor. What changes is the voltage. The voltage gets divided when it goes through each resistor and then coming finally back to the original source. So another name for the circuit is called a voltage divider. A voltage divider. And again, that's because as the voltage goes through each resistor, the voltage drops. So that's why we need to find V1, aka the voltage drop across R1. So what's the first step? So what we can use actually is something called Ohm's law. Ohm's law states that voltage in a circuit is equal to the current, the flow of electric charge, multiplied by the equivalent resistance. What is an equivalent resistance? The equivalent resistance, you can think about it as the total resistance in a circuit. But more specifically, it's a value that represents all the resistances or the resistors in a circuit in basically one value, without changing any of the functionality of the circuit. So our equivalent or equivalence resistance is going to be representing R1 and R2 together. Now, we can actually apply Ohm's law to every other voltage in here as well. So we can actually say that V1 is equal to the current, and again, because it's a series circuit, we know that the current is unchanged, so the current remains the same throughout the entire circuit. So V1 is still going to equal to current times R1. So it's not going to be R equivalent, it's just going to be R1 because we only care about resistor 1. We only care about the voltage drop across resistor 1. And we can apply the same exact logic to voltage drop 2, V2, and we can say that it is equal to the current times resistor 2. Now, what we don't know here is we don't know the equivalent resistance and we don't know the current. So we can't really find V1. Now, there's a couple things we can do. So we need to find equivalent resistance and we need to find current. The way we can find equivalent resistance is something called Kirchhoff's voltage law. Kirchhoff's voltage law, or more commonly known as KVL, we're going to write it down here. All it says is that the algebraic sum of all voltages in a closed circuit has to equal to 0. Okay, what does that mean? So that means that all the voltages in this circuit is going to be equal to 0. If you add them all up together, it has to be equal to 0 because the circuit is in a loop, is in a closed loop. So how can we actually write that down? What does that look like in equation terms? So following KVL, we can say that we have 3 voltages here. We have the original source, so we have V, and V plus, now we have V1 and V2. But remember, the voltage here is going to be dropped because the voltage is being divided as it goes through each resistor. So this is actually going to be technically a negative V1. So it'll be V plus negative V1. And then we have plus, same thing with V2, negative V2. And these have to equal to 0. And using this equation, we can just simplify it and say that voltage source is equal to V1 plus V2. Boom. That's all KVL is basically saying, is that the algebraic sum is equal to 0. Therefore, the V, the voltage source, is going to have to equal to the voltage drop of V1 and V2. So when we find the voltage drop between V1 and V2, it has to equal to 12. So let's actually plug this in. If you pay attention, we have all these voltages, all their values here. We have them right here that we can plug in here. So we know that V is equal to current times equivalent resistance. So let's write that down. I equivalent resistance. And that is equal to I R1. And then this is going to be plus I times resistor 2. Now, this is just kind of algebra. If you pay attention here, current can be factored out, and we can simplify this equation to just get R equivalent by itself. So let's do that. So we have I R equivalent is equal to, then we have I factored out, multiplied by R1 plus R2. And now we can divide both sides by the current. So now we get R equivalent is equal to R1 plus R2. Simple. So boom, we just found another piece of the puzzle. So using Ohm's law now, we know what R equivalent is. But what is I? So what is current in this case? Now, we can't actually use this equation here, even though we know R1. We don't know what V1 is. So we're forced to use this top one here because we know what the voltage is, the voltage source is, and now we know what R equivalent is. And if we just rewrite this guy, super simple, we can say that current is equal to voltage divided by R equivalent, which in this case is R1 plus R2. So R1 plus R2. Pretty straightforward so far. And that's our current. So all we have to do now is plug this current into this equation, because this is the equation for V1, for the voltage drop across R1, V1, and that's what we need to find out. So if I bring this guy down here, let's go over here, we can say that V1 is equal to, I is equal to V over, and then we have R1 plus R2, both multiplied by R1, which is in our original V1 equation. Now, if we make this look a little bit prettier, we can say that V1 is equal to V times R1 over R1 plus R2. And now we have these values in the original circuit that we can plug in and find what the answer to V1 is. So we know that R1 is equal to 3 ohms, and we know that R2 is equal to 6 ohms. And we know the voltage source is 12, so 12 volts. So now we can just plug these in. We can say V1 is equal to 12 times R1 is 3 ohms over 3 plus 6 ohms, which is R2. So this is just 9. 3 over 9 is just 1/3. So we have V1 equal to 12 times 1/3. So then V1 is going to equal to 4 volts. And that would be our final answer for V1. So the only other kind of shortcut that you can use is that because we know for certain that R1 and R2 are in series, we can actually kind of skip this KVL step here where we did all this algebra and just straight go to here, because in series resistors, R equivalent is always going to be just the two resistances or more just added together. So if you had like resistor 3 down here where they were all in one line and then in a closed loop, it would just be R1 plus R2 plus R3. So you can't skip that if you know for certain that you have a series circuit. So we have the exact same circuit in Circuit Lab here, and we can simulate it to see if what we found is right or not. We're gonna grab what the voltage is before hitting the first resistor, and then also the current, and then same thing after going through the first resistor. So we have the voltage after and the current after, and then we have the voltage after the second resistor. So if I run the simulation here, it's going to fill these values and we can see if this is correct or not. And boom. So before it goes through the first resistor, we have 12 volts and our current is 1.3 amps. And then after the first resistor over here, we're going to have 8 volts. So if you remember, the voltage drop V1 was 4 volts. And if we do 12 minus 4, boom, it's equal to 8 volts. So that means our calculations are right. And something else that's cool is that, again, our idea of the series circuit was correct in that the current is completely unchanged going through this resistor. And then finally, once it goes through the second resistor afterwards, the voltage is actually 0, which again makes sense because it complies with KVL. And the voltage drop of V2 through R2 V2 is equal to 8, because beforehand it was 8 voltage, and then after it's equal to 0. And that's it.